Hi there, good afternoon. Let's try that again. Hi there, everyone. I just want to check and make sure that I am audible. So if I can just get a yes or an okay, or we hear you in the chat, and then we'll just get started. All right, cool, awesome. I've got one yes, so I'll just kind of go ahead and get started. So as I mentioned, for some of you who just joined us a little recently, my name is Kamanthi Jacoby. A second year medical school student. Today's actually the first day of MS2. Second year medical school student at SUNY Downstate in Brooklyn, New York. Attended Duke University and studied biomedical engineering. Took the post-bac route to med school and was a career changer before applying to medical school. I've spent some time as an educator. I love to tutor. And so tonight, what I really hope to do is kind of go over some physics stuff with you guys and maybe kind of get into a little bit about Mcat studying. So I always like to start off with this slide anytime I have one of these free sessions, because I think it's important before we really like jump into studying Mcat physics to kind of have an idea of what exam you're going to take and what the Mcat really tests. So I'm going to go through a few things that you might be doing wrong that, well, not doing wrong, you might just be doing and not really realize that there's a different way to do it that can ultimately kind of accelerate you to towards whatever score you want to get. So the first thing that I'd have to say in order to kind of explain to you what is it that you're currently doing, why you should change it and what the benefits of changing it are, is I first have to kind of articulate to you what the Mcat is all about, at least as I see it. So to me, the Mcat is not about science. It's really an exam that's meant to filter out of all the potential applicants into medical school, who's prepared to receive a clinical reasoning education the first day they show up. All right, so let me say that one more time. It's not about science, it's not bio or orgo, or even physics, which you're here for today, honestly. This exam is really testing whether or not you have whatever makeup, whatever thing it takes for you to be prepared on day one, like right after you get your white coat on, to begin receiving a clinical reasoning education. And the reason I came to that conclusion is I personally went through my first year of medical school and reflected on my tutoring experience, tutoring Mcat, or my time taking the actual Mcat. I realized there's a lot of similarities, both in terms of the way the Mcat was structured, right? The passage-based approach is very similar to what we get in medical school and what you would have to do as a practicing physician, right? If you think about it, last doctor's visit you had, right? What did you do? You provided the doctor with a whole bunch of stuff, right? It hurts here. It also hurts over here. My cousin has this. My grandfather died from it. What about this? I WebMD'd, right? You told them a bunch of information. And among the things that the doctor, whatever type of physician, or even physician assistant, nurse, whoever this clinician was that you saw, had to listen to you, right? Distill what's the most important things that you're saying, right? So for example, if they were trying to think about the symptom that you're describing, what are the 7 dimensions of a symptom, right? That way they can decipher what is it that you said, arrange it in a way that they can easily use to start to reach back and think about all the patients that they've ever seen, all the books and all the chapters on whatever condition you might have. And ultimately, they're going to come up with a differential, which is their best guess of their attempt to synthesize all this information, right? I begin here in order to get across the point that as some of you who've done Mcat, either taken it before, are currently taking full-length exams, are curious about the Mcat, wherever you are, right? At some point, you've looked at an Mcat passage, and it's important for you to start to realize that the Mcat passages are specifically designed to get at your clinical reasoning, critical reasoning, sorry, and not really your science content. So if you're doing some of the following things, you probably aren't allocating your time effectively to really get at the actual goal or the learning objective or the evaluation objective of the Mcat, which again, critical reasoning. So some of you guys might be doing just way too much content, right? Like you might just be holding on to the guardrails, you got the training wheels on, as I say, you just are in Khan Academy, you're looking at your notes, you're reviewing your outline, but you're not doing any practice passages outside of doing full-length exams, right? Which means you're only really spending a small amount of your week on doing the actual portion of your studying that replicates the actual exam. For those of you that are actually doing some passages, maybe you're not actually reviewing them, right? It's important that you stop and you reflect on the mistakes you're making, why you're making those mistakes, and then come up with a plan for what you can do next to remedy them, right? That might be going and looking at a video. It might be doing more practice problems. It might be attending a private tutoring session, right? It might be whatever it is, right? But you first have to start off by getting off the content, do practice passages, review them, so you ultimately can start to like make a list of your mistakes that you're making, right? So some of you guys probably already doing that. You're like, I've got a document that I keep, but you're maybe just doing like a really superficial level review, right? I'm gonna say something that I say every time I do webinar sessions to kind of explain what I mean by superficial review. So I think AMC explanations are amazing. That's my hot take. I typically like to say that and I can kind of wait and see how long someone's gonna get comfortable enough to just say something in the chat about that, right? So I think AMC explanations for questions are amazing. Who agrees or who doesn't agree? I'll give y'all like 25 seconds to kind of get bold and say something in the chat. Or you can unmute yourself and say something if you really agree with me that an AAMC explanation, if you've ever looked at it. All right, so I got Katie says she doesn't agree. Marissa doesn't agree. Megan says she agrees. It allows you to think like the test maker. Interesting. Right, so I'm going to pause here and kind of talk why I think what Megan says is actually spot on what I wanted to get across, right? So let's think about an Mcat passage, right? So you guys think about any kind of Mcat passage, right? How many questions are typically on one? Just answer in the chat or somebody unmute themselves and let's just be a little bit interactive, right? 6 questions, right? 5 to 6, let's call it 6. Typically it's about 6 on average, right? So 6 questions. How many discrete questions do we typically see in a passage, any kind of passage on average? 2, all right, got a couple 2, a few, okay? On average, it's about 2 per question, 2 per passage, right? So 6 questions in each passage, and we already know that 2 of them are gonna be discrete questions that you just need content to know. Great. The other 2 types of questions, does anybody know what those types of questions are called, right? The other 66% of the passage, right? What's the AMC call those types of questions? Critical reasoning, skill reasoning through, reasoning about the experiment. Okay. Any other guesses? Any other guesses? All right. So everybody's kind of spot on, right? Like you guys picked up on the fact that the other 4 questions are about critical reasoning. So there's going to be an explicit question, right? It's explicit because it's literally telling you what is explicitly stated in the passage, right? So typically you're going to get 2 of those questions. Again, remember, how many questions per passage? 6. We've already counted for 4. 2 of them are discrete questions. You only need content. 2 of them are an explicit question that asks you what's in the passage, right? So a lot of how this is going to be phrased is based on the passage, what can be concluded, right? That's literally telling you, look at the passage, look at the data, the answer's there. The other more difficult question for some of people is implicit, implicit questions, right? So implicit questions, the task around an implicit question is take something that is outside the passage, and your goal in answering the question is to make it fit. And maybe as we go through some questions today, we'll actually explore these kind of questions, but we're really just only doing an accounting. 2 more questions. So we said 6 questions per passage. 4 out of those 6 were critical reasoning questions, right? I made this point to kind of get across what I believe Marissa said, right? Somebody said in the chat, right? AMC explanations are great because they tell you what the actual question was about, right? So if you've ever not been able to understand an AMC question and gone to Reddit, right? You just tapped out and like couldn't really get to what the learning objective of that question was. because it was most likely a critical reasoning objective. And you took a superficial approach to studying because you only explored the content part and you really didn't stop and say, let me reason through this question, right? Maybe it's not really an orgo question. Maybe this is a question about how do I use my organic chemistry knowledge to create an experiment that can identify what the leaving group is on a particular reaction, right? Maybe that's what the question's asking me, right? And I can reason through it by applying my knowledge. So when I say maybe you're reviewing your passages where you're doing it superficially, right? You got to ask yourself, if 77% of the exam is about critical reasoning, how much of your own time are you actually allocating either in your studying, your practice, preparation, or review to that portion of the exam? So again, maybe you're doing too much content. If you're doing passages, maybe you're not reviewing them. If you are reviewing them, maybe you're doing it at a superficial level. But even if you are actually digging into it and making really decent, like deep, insightful, like noticing actual trends and stuff about your test taking, maybe you're not documenting it. And I believe like it makes sense, right? If you don't document it, it didn't happen. If it didn't happen, you didn't learn it. If you didn't learn it, you then just never got it, right? So my whole point in saying this is a lot of what I'm going to teach you in the actual passage section is going to rely a lot more on the critical reasoning side of things. And yes, there's going to be physics that's taught, but the physics that's taught is really going to be from the perspective of how do you apply it, how do you reason through it. So that's always my spiel, because again, I think you guys noticed I said this is really not a content review session. This is do a practice passage, and let's talk about how we got to the answer of the actual practice passage. Okay, so in this deck, I'll send this out. I talk about how I studied for the Mcat tracker that I used. I leave some notes about biochem. I go over a passage. So I actually do a free session that's similar to this for biochem, but we're gonna click ahead and we're gonna come to here. And we're gonna go here, right? So we're gonna jump in and we're gonna talk about like the ChemPhys section and the most common type of practice passage, or passage generally, I guess, that you're gonna get on the chemistry and physics section. It's similar to what you're gonna get in biochem, but a little bit different, right? So it's known as the informational passage, is like how AMC like defines it. And for me, what the informational passage means, as far as like I understand it, right, is it's just gonna give you a straightforward presentation of scientific information, oftentimes that you already know, right? So that's a key thing. You might already know the information that they're giving you in the passage, because again, it's a informational passage. Key thing to remember as we talk through this. So the passage might be, sorry, is there someone that is annotating on the screen? If so, kindly ask that you do not do that. Try that again. So informational passage, right? They're going to give you information, scientific information that you probably already know, right? So if you're in chemistry and physics, they literally might tell you about a periodic trend, right? They might tell you about electronegativity, right? What are some things that we already know about electronegativity, guys? So like this is the collaborative part. So unmute yourself or in the chat, just start to throw out random things you know already about electronegativity. All right, so I got like a redox in there. I got the trend line on the periodic table. I got something about dipoles, right? We're sourcing some stuff. I heard fluorine is the big one. Let's see if we can get two more things. Polarity, right? Oh, Fonkelbrish, great. Fonkel, we can stop there. Fonkelbrish, right? So I know I didn't spell that right. So the point I'm trying to make is there's a passage out there that exists, that is an informational passage that is looking to simply present information about the electronegativity, that concept, right? They're going to create a passage that has some kind of experiment that is in some way going to present to you or actually confirm in data form something that you already know. Why? It's an informational passage that intends to inform you on some scientific thing in chemistry or physics that you already know. For example, it might be a presentation, it might be a passage that's really only talking about the trend line on electronegativity, right? Which is basically Fong, Rish, right? So this might be the key information, the straightforward presentation of scientific information that you already know. That might be what they're looking to do and tell you about, right? So is anyone willing to kind of hop on and just kind of talk for 30 seconds to 45 minutes through a hypothetical practice passage that we're going to make up right now? And the goal here was trying to kind of drill home what type of informational passage, what an informational passage is. So Megan, you want to just unmute yourself and just chat? So introduce yourself, say where you're located.
Sure. Hi, my name is Megan, and I'm currently doing a non-thesis master's at Texas A&M, which is located in Texas.
Nice. Texas A&M in Texas. Awesome. So we sourced a couple things earlier, right? So we sourced that electronegativity had to do with, I think I got polarity. So the word polar came up. We got trend lines. We got, what else did we get? I got fluorine just came up as a word, right?
Right.
We also got dipoles, oxidation, redox, right? So we can stop there, right? So this is going to be your grab bag of this hypothetical passage we're going to make, you and I, right now, okay? So which one of those things that are sort of related to the idea of electronegativity do you want to talk about?
I guess redox and polar.
Polar. Let's go with redox because redox is always trippy. So we're going to talk about redox, right? So remember, the information that we're trying to get across is about your understanding about electronegativity, but we're going to specifically use redox, okay?
Okay.
So are you Leo goes grr or oil rig type of person?
Oil rig.
Oil rig. All right. So oil rig. All right. So when we say a reduction, what is happening there?
Our compound or atom is gaining electrons.
Gaining electrons. What is it losing? Also, just as a kind of review for anyone that's out there, quick little tip.
Sure. Oxygen?
Losing oxygen bonds. I just dropped this here as a little like major key. So I'm just gonna drop like little like major keys through. I'm really mad corny, so it's a DJ Khaled reference. So some major keys of like things that you might want to write down that help out. So if you ever get stuck on a problem, you don't know what redox, whether it's redox or oxidation, just count the number of oxygen bonds. So that to that is a reduction because you went from like 2 oxygen bonds to 1 oxygen bond. So that's kind of an aside from our broader lesson. But back to what we were talking about, this passage we're making. So we've got an idea of what we are talking about. So reduction is to gain electrons, right? And so what is oxidation?
Losing electrons.
Oxidation is to lose electrons, right? All right, cool. So now that we've got that, right, let's get our grab bag of like just concepts, right? So redox concepts, let's just kind of source a couple like more finer details about redox stuff that we know, right? I'm going to throw the first one out. And then you guys just kind of start to throw some stuff out about redox generally, wherever your brain goes. We're trying to get a like nice little collection of specific concepts to add on to this fake passage that we're building.
Can I go ahead?
Yeah, go for it. You're on the line. It's you and I.
Yeah. When I see that, it reminds me of Mcat minus E, like E cathode, energy of cathode minus like E, anode. So, and I know that the more positive the reduction potential, that shows that our, atom wants to gain more electrons, which is more it's a sign of like higher electronegativity.
Awesome. And then let's do the opposite.
Like E
so
off?
if you EOX, right? Give me the sign convention on EOX.
See, I usually like worked at the redox. Okay. I'm assuming like the more positive, the more oxidized something wants to get, so that the higher chances of it losing electrons, right?
Yep.
Okay.
But we're just gonna, for the sake of today, just gonna keep that sign blank for right now.
Okay.
Right. So another learning lesson for physics that I'm gonna pause here and just kind of teach you guys and kind of bring up is you want to get, I call it equation intuition, right? At the moment, we don't really actually haven't double checked to see if what you told me about E redox and E oxidation is correct or not, because I honestly don't remember the sign conventions, but I think through the logic of it, right? So by the end of it, we're probably going to think through it, and if we need to for this fake passage we're making. But as a general rule of thumb, when you do physics, for example, great example is I'm going to start writing down an equation, and anyone want to help me out finish this equation? I think there's an R to the fourth up there. There's an L there. Anybody? Am I like? And I think there's an 8 right there, right?
Yeah.
What equation? What equation does that describe?
Yeah,
Poisson's law, right?
Yes.
So I was a biomedical engineer in college, and like we use this exact equation to do like microfluidics, and I still don't remember the equation, simply because all I know is my flow rate has to be proportional to my pressure head, right? The diameter of the thing that I'm pushing it through, right? It's got to be inversely proportional to the viscosity, Y, honey, water, right? And then I know if it's a really long tube, obviously the flow rate's going to be like, it's going to take more work to get the thing all the way to the other side. So I know whatever the length is going to be there, right? So in my head, this is what I see when I think of this equation, because I've gained equation intuition by asking myself, what is the consequences of each one of these symbols? So that's a major key, right? So sorry for the sidetrack, ladies and gentlemen. We're going to go back to the passage that we're making up, right? So now for anyone that has actually been looking at the AMC passage that we're going to do, if you actually stop and look at the experimental setup, you take a second and you notice what kind of fake passage Marissa and I have. I said that correctly, right?
It's Megan.
Megan, sorry. I'm so sorry. I'm looking at my chat and Megan, I apologize. So Megan, you and I are kind of making up an informational passage together, right? So I gave you guys a hint, right? Do you have the AMC passage in front of you?
Yes.
You do, right?
Just to make sure it's the bank, right?
Yeah. So you go ahead and look, and I'll just kind of click over and show everyone the passage. So we are all on the same page.
Okay.
All right. So it's on the screen right now in the Zoom. All right. So remember, what was the topic we started off with?
Redox and
electronegativity was the thing that we needed to know. And then we picked redox as the thing we wanted to talk about, right?
Right.
And then we talked about reducing potential. And you basically told me that's kind of like proportional to electronegativity.
Yes.
Right? It's how much you want that thing back, right?
Yes.
So we're going to look at this practice passage, and we're only going to focus on, we're only going to focus on this part of it, right? And what we're going to try and do is we're going to take the information that we already know, right? And make it into a practice passage together, okay?
Sure.
So in order for something to be reduced, right, what has to happen to its electrons?
It needs to gain electrons.
It needs to gain electrons, but those had to come from somewhere, right?
Yes.
Right, cool. So you know how sometimes we like reverse the E reduction potential equation and like flip the sign on it?
Yes.
Let's just do that in our head mentally, okay?
Okay.
So we're going to stop really thinking about the reduction potential and kind of think about it more in the oxidation side of things, right? So when something is oxidized, what happens to it?
It loses electrons.
Loses electrons, right? So what's a nice way for us to use, what can we use to cause something to lose electrons?
I know if we use a metal, they're very prone to losing electrons.
Using electrons, and what kind of energy source might be a good thing for us to use to pry out a electron?
Uh, like heat or
Heat is one. Perfect. Heat is one. What's another one?
light.
Light is the other one, right? Have you ever heard the term ionizing radiation?
I believe so.
Ionizing radiation, perfect. So if I was talking about ionizing radiation, how would I go about figuring out how much energy is in that light? What's like the equation I would use?
Uh,
It's like energy of a photon, right? Planck's
HF. Wait,
constant,
yeah,
HF.
yeah.
Right, cool, awesome. So let's pause here and kind of do a little quick talk about, let's do a, Marissa, whoever's asking, it's the section bank, Chem Phys, the very first passage. It's on the screen in the Zoom if you want to follow along that way. All right, so Megan, you still there?
Yes.
All right, cool. So so far we said we're thinking about making a passage that tests electronegativity, right? We decided let's focus on redox, and we said we kind of know that the trend line between redox potential is kind of related to electronegativity, but then we said let's just kind of, for the sake of this experiment, we're going to reverse our thinking and kind of think about how oxidized can something get as a way of telling us the inverse of how reduced it can be, right? So let me pause here and say something, right? If something can be really oxidized, right, what does it tell you about its ability to be reduced? Can it really be reduced?
No.
No, because if you're a molecule that loves to lose electrons, right,
Yeah.
Leo or oil, you're oxidized, you're probably really bad at being reduced, right?
Uh-huh.
Cool. So the reason I made this point here, and I'm taking this weird kind of twisted route here, is one thing the AMC loves to do, especially in the Chem Phys section, is to reverse your thinking that you normally think through, right? When we mentioned electronegativity, you thought pull electron, right? When we thought redox and the reducing potential, you really switched to the convention, which is really about gain electron, right? But what's the ultimate focus of this passage? Talking about electronegativity, right? It doesn't matter which side of the coin I look at electronegativity from, right? If I'm looking at it from the oxidation side, right? If you're an electronegative molecule, you do not want to be oxidized, right, Megan?
Right.
And if you are a really good at being reduced, you don't want to give up that electron, right? Your electronegativity is high. So the AMC is going to set up situations where the way your brain normally thinks through as you study information is you're going to require reversing your thinking in order to critically think through the passage. So this passage that Megan and I are hypothetically creating is a passage in which we're going to use ionizing radiation in order to study whether or not different samples, right, of something, we don't know what that something is, but let's say we've got sample A, B, C, and D, and we're ultimately curious about two things: the electronegativity of those samples, but the data we're going to create is going to be really around reducing potential, kind of, right? So Megan, I'm going to just have us pause here and get back to kind of reconnect to the teaching point I was trying to make. But do you have any questions sort of about kind of the learning exercise you and I have been doing, or the sort of point I'm trying to make about, or any of the points you think I'm trying to make about the type of passages that you're going to see on the Chem Phys section?
Nope, so far so good.
All right, thank you so much for volunteering. That like, I would not have done that. I'm not that brave, so thanks again for trying out that. So just mute yourself, and then I'll just go ahead and clear my screen. And what we're gonna do, actually, guys, we're gonna take a journey backwards, right? And kind of talk about why I did that little exercise, right? So what we were trying to do is we were trying to create an informational passage that provided you a straightforward presentation about scientific information that you already knew. That was electronegativity, right? We had to figure out what the main topic was going to be of the passage, right? It's typically going to come in the first or the beginning of the passage, right? Because ultimately what I was trying to get at is there was a set of independent variables I was trying to I was interested in learning something, an independent variable. In this situation, the independent variable was I had sample A, B, C, and D. Those were the things I was looking to study, right? So from the beginning, I was looking to inform you by presenting you with a straightforward representation of scientific information you already knew about electronegativity, right? The independent variable, or the thing that I was really curious about, was kind of what's the electronegativity or redox, right? Or whatever you can think of as a way to say the electronic structure of those particles. How well are they holding on to those electrons is ultimately the question I was trying to get at, right? So this might be the main topic. The independent variables I'm creating in this fake passage might be the different samples. The outcome, right, the dependent variable, or more specifically, the way I look to measure it, might be by taking the reducing potential, some experiment that I create, or even oxidation potential, depending on how I'm feeling that day, right? Now, the key part of translating all that was you had to integrate the following. I was going to use electromagnetic radiation to ionize something, right? Electronegativity. Remember all those topics we came up with? Periodic trend, redox, thermodynamics. Right, somebody's asking thermodynamics, what do you mean? Delta G is equal to negative N F E redox. That is a thermodynamics concept, right? So you understand that this ionizing step here, when I'm pulling the electron, right, where I'm actually studying the main topic, the electronic structure of whatever type of samples, independent variables I have, right, can really tell me a lot of different concepts. So the AMC can write a bunch of different questions to test your understanding of all those concepts in this example. I ionize that thing, my little electron is going to pop off, right? That is the photoelectric effect. In order to understand that, I have to understand thermodynamics. What do you mean I have to understand thermodynamics to understand the photoelectric effect? Well, the photon came in with some amount of energy. That amount of energy had to be used to overcome the work function, which is what? How hard the nucleus is holding on to the electron. Whatever excess I have is just going to be the kinetic energy that's transferred to the electron. Okay? So again, I'm just going to clear out some stuff and just kind of make sure you guys are following along as I create this fake passage in order to kind of give you guys a unique roundabout way. So instead of me walking through these steps, I'm kind of showing you how these steps kind of come about, right? So again, Megan and I were looking to inform you by giving you a straightforward presentation about some scientific information that you already knew, electronegativity, right? We had a main topic that we were really interested in learning, which is just the electron structure, the electronic structure of something. We had some question about the electronic structure. The independent variables that we were looking to kind of look at were the different samples, right? Is it a sample of like tungsten or whatever, right? And the outcome we were looking to use to measure, at least we're not sure yet, but maybe we're going to use reducing potential because we kind of know how that relates to your ability to be to have an electronegative molecule. Or maybe we're going to use oxidation potential, right? Or maybe we're going to use an electric field to calculate that outcome, right? So now I added a third thing. I said electric field. How are we going to use an electric field to figure out what's going on at this ionization step in order to study electronegativity, some periodic trend, something about redox, maybe something about thermodynamics? You might imagine a situation where you set up an electric field in this experiment. And what's the equation for like the force? Anybody that an electric field, like what's the electric field? The force on a particle, a charged particle, that's an electric field. Anybody? Just shout it out, please. It makes it easier. QE, right? QE, there you go, right? So the point is, we kind of know what the force on a charged particle is. So maybe some crazy passage says, hey, let's figure out what the electric field we're going to have to put here in order to finally ionize this, right? Because maybe the photon that we used wasn't quite strong enough to get over the work function, right? So I'm going to pause here, right? Because I might have twisted some of you guys up in knots, right? And the whole point wasn't really to twist you up, was to kind of just show you how a ChemPhys passage is structured. Okay, so I'm going to pause here real quick, and I want to take some questions before I kind of go through from the beginning to the end, and then we're actually going to do that passage that's up next, which hopefully should feel and sound and look a lot easier, having gone through this kind of breakdown of this approach. So anybody want to just ask a question out loud, please, if you don't mind? Marissa, feel free if you want to ask your question, or I can ask it out loud. Okay. So Marissa asked, how do you recommend we improve our ability to intersect different physics topics together, right? So the main way is you have to do passages, right? And the more you do passages and look at them on a content-specific level. So you would have seen wherever I posted, however you found out about today's session, a list of recommended passages based on topics. As you do, for example, a bunch of fluids questions, you'll slowly start to pick up on the fact that like there's a bunch of common trends of topics within fluids, right? And different example types that get across at the same exact topic, right? So today's passage, the way I was able to make it is because I know there's a common pattern: electronegativity, ionization energy, periodic trends, redox, are all things that are commonly tested by the Mcat, right? I know that because I studied all of those individually and noticed from doing the pattern, the practice passages, that wait a minute, these topics tend to blend in together. That's kind of how you start to blend and figure out the best way to integrate this stuff. And I usually talk ad nauseum and say the same thing. 70% of the exam is basically critical reasoning. So the best way you improve your physics section is not by doing physics questions, but do practice passages. And as you're doing them, right, you want to, and like you're reviewing them, as you're reviewing them, you want to ask yourself, yeah, do I get the physics concept right? But can I critically reason through that experiment that's the crux of the next passage that we do, right? Because that experiment that you see on the next passage, I guarantee you today, I'm only going to bet $10, but I guarantee you that passage is going to be, that setup of that experiment is going to be on your exam, whenever that exam is. If it's on Friday, if it's in a week, if it's in a month, right? If it's next year, you're going to get a passage that looks like, or has an experimental setup that looks at checking your understanding of the properties of light, right? The properties, chemical properties of electronic structure, and some physics concept related to electrostatics. So just do passages. Any other questions? Okay, wonderful. So I'm going to go through these steps again as I see them. This is kind of a draft version of this. But I encourage people again to think of this as a list, not steps. Because if you think of it more as a list, it's going to help you manage your working memory. In order to not spend your time thinking about 1, 2, 3, 4, you can just spend your time thinking about what is it that I have to find out about a passage, right? What are the 7 things or whatever number it is that you have to find out about a passage to know everything about it. So for ChemPhys, the number 1 passage type right, is going to be an informational passage. That's going to be a straightforward presentation of scientific information that you already know, or this is where it gets tricky, a physical phenomenon that can be described or understood by some specific information that you should already know. So they can tuck it in by giving you some phenomenon, right? The Northern Lights. They can give you a whole passage, a paragraph that talks about the Northern Lights, and then give you the information that is straightforward about the scientific information that explains the physical phenomenon they're giving you, and then expect you to critically reason through the experiment or understand the data and the physics behind it to answer some discrete questions, right? So it's key to remember that sometimes they can tuck it as a physical phenomenon. You want to make sure you know what the main topic is, right? So that passage that Megan and I made, the main topic wasn't really electronegativity. It was the electronic structure. Right? Because electronic structure captured that big bag of redox, some thermo stuff in there, right? We covered, what do you cover? Periodic trends, right? We covered photoelectric effect, right? The main topic had a whole bunch of specific parts to it, right? So here's another major key for when you're looking and reading a passage and you know, okay, I get it's something to do with electrostatics, but what specifically are they trying to actually understand here, right? Here's a major key. You're going to look for terms like to analyze, to determine, right? Sometimes the hypothesis might literally tell you what they're specifically trying to do. Analyze, investigate, to investigate is another one. These are phrases that when you look through a passage, tell you the specific part of the main topic. All right. So from here, my recommendations, right? So all you've done so far, you've read like the first 1 to 2 paragraphs, right? End of the first or beginning of the second. And you've picked up what the main topic is. You've used your major keys to figure out the specific part of the main topic, right? The rest of the work is kind of easier, right? You got to figure out what the outcome is. I like to find the outcome first because there's only ever one outcome in any experiment, right? You can easily find it in the y-axis of any data they give you. Or a major key is they might literally say to measure as a way to find out what's going on. Okay, so I'm gonna clear and get across a couple more, like these are like some very, very high yield granular things. So the concept of understanding how you measure phenomenons is super duper important. For biochem, what that means is know your lab techniques. If you know what your lab technique is, you are going to understand what outcome or what dependent variable somebody was trying to check and see, right? But on top of that, if you have a good understanding of your physics or your chemistry, right? If you understand the concept, right? You can understand how it's being applied in a situation, such as the example that we made, in order to measure a certain outcome, right? Remember the outcome we were really looking at was kind of the electronic structure of the atom, right? So again, we're trying to really talk through how to integrate your critical reasoning on an informational passage. Because ultimately, every passage on the AMC is going to boil down to some type of independent variables. And they're going to try to test and see if you understand the relationship between those independent variables and the passage's main idea. Okay? So that is about 45 minutes of me kind of explaining and talking and teaching. We're going to go ahead and put up the actual passage that we plan on focusing on today, right? I'm going to give us until the 7:15 mark. I want you guys to now take a look at this passage. If you have the AMC material, just go ahead and actually try the questions. Now that we've all kind of talked and had this collaborative experience of thinking about what a ChemPhys passage is really about, take 15 of independent study, and then we'll regroup, and then I'll ask a couple volunteers. I believe Andrew had actually said he'd volunteer to help break down the passage. So we're going to break down the passage together, and then if we have time, maybe answer some of the questions. So 15 minutes, and I'll be back at the 15 mark. Thanks. All right, as you guys are kind of working through the passage, if you start to have questions, go ahead and start to drop them in the everyone chat. That way we're gonna have a good list of questions that we can go ahead and use to structure our learning for the next 45 minutes or so. Also, if you've already gone through the passage, do the questions as well. I don't know if I was that clear on that. So I'm not sure if we're going to get to go through all the questions together, but do them on your own right now, because why not, right? Why waste the time? Okay, awesome. So I haven't really got any questions yet. So I'm assuming that you guys just looked at this passage and it wasn't that hard. So Andrew, I believe, Andrew P., you said you were up for just kind of helping walk us through this passage, right?
Yeah, sure.
All right, cool. So we're going to walk through the passage. And remember, what we're really going to try to figure out is what information do we already know, right? Because it's an informational passage, right? What's sort of like the main topic, right? Or concept, maybe might be the word concept, might be the word we want to use. And then we got to figure out what are they looking to analyze or to determine, right? Analyze. And then we might have to find out the outcome, which is a dependent variable. And then we need to find the independent variable at some point. We need to predict the relationship that's going to be there. And then ultimately we need to confirm it somehow, okay? So this is the 7 things that we got to do. So we're gonna go together paragraph by paragraph and like kind of talk through things, all right? And then kind of see what we get, all right? So I'll let you just kind of take charge. I'll read and you kind of tell me what's important from each paragraph, right? So the first paragraph, so MALDI is a soft ionization technique used in conjunction with mass spectrometry to analyze proteins, protein fragments, and peptides. In MALDI, a protein containing the sample is coated with DHB, a structure shown below, and the coated plate is subsequently subjected to a pulse of electromagnetic radiation, whose characteristics are summarized in the table below. All right, so Andrew, just kind of walk through all of that, and just take a second if you need to read it on your own. But ultimately, what I want you to do is just summarize it for me, right? But kind of summarize it for me in the context of some of these things that we have on the right side, right? Whatever that looks like, we can talk through it together.
Okay.
So we can start here. What would you highlight? What stood out to you? What would you highlight initially?
So in the first paragraph, the thing that I would highlight is where it says to analyze proteins, protein fragments, and peptides,
Right? Why would you do that?
because that's kind of telling us what they're looking at, what they're looking for, and specifically what MALDI might be doing. So step
Cool. They
3.
just kind of told us like the specific part of whatever like the main topic or idea concept they're going to do. They're ultimately going to try and figure out like something about those peptides. We don't know what it is. Is it the mass? Is it the charge? Is it the shape?
Mhm.
We're not sure yet, right?
Mhm.
What else from this paragraph stood out to you?
Aside from it being connected to the structure of DHB, it is introducing a new technique. So what MALDI is in itself.
So what is MALDI? What does MALDI mean?
Well, so it says the breakdown, but it's saying that it's a soft ionization technique with mass spectroscopy.
Cool. So let's dig into that. So soft ionization technique, right? What does ionization mean to you?
Having a charge being coming as a result, like coming off
Right.
of something possibly.
Suppose if ever we just call it just take electron,
Okay.
right? So basically, it's this process, the first part, you're going to take some electron from somewhere, right?
Mm-hmm.
And then mass spectroscopy. What do you remember or know about mass spectroscopy? What is it used for?
I'm pretty sure it helps separate things based on, I want to say weight. I don't know why I want to say weight.
Yeah, it's size, because the first
Size.
word in it is mass, right? So let's kind of take a look at the 3 things that we have written down. Let's look at them all together, right? So it's some technique that's first going to take some electron off of something, and then it's going to also use some other technique to check the size of this thing. And ultimately, the goal of what they're looking to do is they're looking to analyze the size of these fragments. All right, sound good?
Yep.
All right, cool. Now let's talk about this DHP guy, right? So you look here, anything come to mind initially?
That's carboxylic acid, aside from that, and then not really.
Nope, not really, right? So we read ahead and we see this piece here, right? So talk to me about this. What does this mean to you when you see this? That the coated plate is going to be subjected to electromagnetic radiation.
That it's going to undergo, coated plate is subsequently subject to pulsed.
Remember, what was the first thing that they did in MALDI?
In MALDI, they just use a technique to just analyze the protein fragments and spectra. The soft.
Remember the first thing they took? They took the electron first.
Okay.
How do you think they're going to take the electron?
How or why? I'm sorry.
How are they going to take the electron?
Electromagnetic radiation.
There you go, right? Okay. So now we figured out a couple things about this passage, right? What they're looking to specifically do is they're trying to analyze something about some proteins, right? How they're going to do it is they're going to take some electron off of something initially, and then they're going to use some type of way to measure the size of the thing, right? We then look over on the next sentence and it tells us the how they're going to take that electron, or they're going to use the electromagnetic radiation to take the electron away, right? I'm talking in this way because at this point, you can kind of already start to inventory topics that we already know. All right, Andrew, what are some topics that we already know that we might have like maybe not seen directly, but kind of activated in your brain, right? So some of the words I used were ionization. I mentioned electromagnetic radiation. I also mentioned mass spec, right? What else got just interesting? Like what got turned on in your brain when you heard ionization energy? What else did you think about?
From ionization energy?
Yeah. Did electronegativity come in mind?
Yeah.
Maybe redox?
Yes. Okay.
Maybe something to do with periodic trends, maybe?
Yes.
Right? Electromagnetic radiation. Maybe you thought to yourself, energy of a photon, right? If energy, light's going to act as a particle, right? Stage F. Or maybe you thought to yourself, all right, maybe this is a kinetic energy type of situation that they're trying to set up because they're going to ionize something. Right? So what's happening if you're reading this way is you've allowed yourself to kind of start playing around with what else could possibly be going on down here, right? We know that they're going to inform us about something that we know, right? So as we're reading it, we're trying to activate and reach back into our brain and think, what else could we possibly be talking about in this passage that I already know, right? And the keywords that we've been looking at and focusing on are words, if you notice, everything I highlighted is a word you kind of already know. Isn't that right, Andrew?
Yeah, in different contexts.
Ionization, you kind of had a working vocabulary of it. Mass spectroscopy, like the idea of electromagnetic radiation, right?
Mm-hmm.
I picked those because I knew what kind of passage this was, right? Do you remember how I articulated what the way to describe a information passage is, Andrew?
A way to describe information passages?
Yeah. If you're gonna say yo, what's the goal or what are they trying to accomplish when they give you an information passage? You'd say what?
They're essentially trying to give you information either on a topic that you already know or show you a different process.
Exactly, right? So we came in looking to see, all right, cool. What do we see in the first paragraph that we already know? We picked up a couple things that we already know, right? We kind of identified that all right, we kind of know what specifically they're looking to do. Whatever the rest of this experiment is about, they're ultimately looking to find something about proteins, protein fragments, or peptides, right? We still haven't figured out the dependent or independent variable, but by looking at table 2, right, maybe one of the independent or dependent variables, the independent variable rather, is the type of light that they use, right? If we look at the picture, maybe this becomes one independent variable. Maybe they go high and low. So Andrew, if I said one of the independent variables was the strength or the energy of the electromagnetic radiation, and I said that energy is going to be low, what color in the visible spectrum would be associated with a very low independent variable or energy of ionization or energy of the electromagnetic radiation, sorry?
A very low amount of energy. So it would be just a general color, or you just want to go from the scale? What do you?
Let's go the lowest of the visible spectrum. What's the lowest energy on this visible spectrum?
Violet?
Violet's actually the highest. Red is the lowest. So here's another quick major key. What's the highest energy level radiation you know?
The highest level radiation from outside of now?
Yeah, just
gamma?
in general. Gamma, right? What's the lowest that you know?
Is that radio waves?
Radio waves. All right, what's the next lowest that you know?
Wow. Is it?
It's in your kitchen.
Oh, microwaves, okay.
Bingo. All right, let's go to the highest side. So gamma, what's one step lower than gamma?
X-rays.
X-ray, right? So remember
Yeah,
X-rays. All right, what comes one step below X-ray?
After X-ray, it's ultraviolet.
Ultra, what color? What was the second part of ultra what?
Ultraviolet.
Ultraviolet. Remember that, right? Let's go to microwave, right? So we said microwave. What comes after microwave? What's the next highest energy after microwave?
Infrared.
Infrared, what color?
Infrared. There. Okay.
Picked up on it?
Mm-hmm.
So now, if you ever get a question that's talking about electromagnetic radiation, right? So this was another teaching moment that I was trying to sneak in here for you, right? Roy G. Biv, right? The red is next to infrared. The violet is next to ultraviolet. And this represents energy of the photon, right? This might be the photon that was released after the electron got excited, fell back down, released some light, right? It could be the color of the laser that you used initially as the input in order to excite it, right? The reason I say that is the Mcat is going to expect you to have a working understanding of the electromagnetic spectrum from high to low, understand how that relates to energy of a photon, right? Now that I told you that, what's the highest energy of the colors?
The highest energy of the colors?
Yeah.
Wouldn't that be what's the lowest for the wavelength?
Right. What's the color? What color has the highest energy?
Violet.
Violet, right? Now let me ask you another question. What has the highest wavelength?
The highest wavelength?
Yeah.
Isn't it? Isn't it red?
It would be red, right? Why would it be red and not violet?
Because they're inversely proportional to each other.
They're inversely proportional to each other. Perfect, right? So I'm asking these questions specifically. And so Carol, I saw you say 700 nanometers for red, right? Quick tip, don't ever memorize the number. Doesn't matter. MCAT doesn't care. Most questions you can answer by just simply knowing the direction of where high and low is based on energy, right? Because if you stop and think about why do they even care that you know the wavelength? They care that you know the wavelength for the following reason. The wavelength can tell you the energy that's in the photon, right? Planck's constant, C over lambda, right? So they care that you know the energy, the wavelength, because they want you to know the energy inside the photon. Why? They expect you to understand the consequences of light acting as a particle, where it can have a specific amount of energy, right? Which we can easily calculate a direction of high to low from red to violet. So answer choices might simply be coded as red, orange, green, and blue. But the answer is blue because the answer to the question was really highest energy. All right, Andrew, you kind of understanding where I'm going by understanding a simple topic of color, right?
Mm-hmm.
What color is on either side, right?
Mm-hmm.
E equals HF, right? A simple formula, right? And being able to use that to know that the MCAT might again test you. Let me make sure everyone's clear. The electromagnetic radiation that they're using to ionize something, they could give it to you in a color.
Mm-hmm.
You guys remember the Bohr's model? You remember the Bohr's model, Andrew?
Yes.
Of the atom?
So. Okay. Mm-hmm.
Tell me a little bit about the Bohr's model of the atom.
In terms of color.
No, not the color. Just tell me basics.
The Bohr's atom.
There's a nucleus at the middle.
Yes.
Right.
Orbitals.
There's orbitals.
Mm-hmm.
Right. And then where's the lowest energy? Where are you going to be at? Where's home base?
Home base would be closer to the nucleus.
Closer to the nucleus, right? I don't think that color is visible. Closer to the nucleus. All right. And then if I wanted to go up to from, let's say, n equals 1 to n equals 2, what do I need?
You need more energy to go to the next orbital.
I need an energy input, right?
Mm-hmm.
So let's see if we can just pause and look at the simple step of things I've said, right? How is this example of the Bohr's model, Andrew, any different than figure 1 that you see in front of you? I mean, you don't have to, there's a small subtle difference, and the difference is the work function for anyone that's really, really trying to dig into the physics. But just think about it critically, right? What's the real difference between the two experiments? It's kind of almost the same, isn't it?
Yeah. Mm-hmm.
Right? Now imagine, right? Let's go back to, remember the passage that Megan and I made?
Yes.
So our independent variable on the passage that we made was just sample A, B, C, and D, right? So instead of having proteins down here, we just had different samples, right? And maybe the question we're asking is, what color do I need to use, right, in order to finally ionize one of these samples? Same experiment, literally using the same setup, right? But I don't have a proton there. I have my samples. I don't know what electromagnetic radiation is, but I tell you that I have a knob that's based on color, right? That goes from Roy, red, orange, yellow, green, indigo, violet, right? So Andrew, what am I trying to get at in this? What's the kind of, what do you draw as a conclusion? Basically from the exercise that Megan had and the exercise that you and I are having. What to you is the thing that is the most salient about those two exercises that we've done today?
I think you're trying to identify how, like with the ideas of electromagnetic radiation, or just electron movement, going back to the ionization technique, that it can be brought to or connect with other topics like Roji-Biv, which has energy being in this proportional to frequency, and how that can connect to different ideas.
So integration would be what you'd say. You felt like we stopped and thought about how do we integrate all these concepts, right? What about the fact that we've made two different experiments, fake passages, one that AMC gave us, and they gave us a beautiful figure, and one Megan and I made up together, right? What do you think about that? The fact that we were able to use the same experimental setup to do it.
So you can like actually,
Go ahead, go for it.
I mean, in terms of how you can use it, you essentially can like find a, like you're saying, a pattern or find a connection. So if you ever see it in different questions or in different ways, you know where to start.
Perfect. So really some of the key things that you can start to do for yourself today to improve your CP score, right, is think about when you study content, are you thinking about how to integrate it all together? And are you recognizing patterns? And the best way to do it is to just stay focused on doing passages, right? But do it in a content specific way, right? This passage is all about electronics, ionization energy, right? But if you were to do a number of passages today about electronegativity, ionization energy, right? Maybe even electrostatics, right? You would, by the time you've done 3, 4, 5 passages, you'd see this experimental setup enough times to begin to recognize the patterns for how it's used and to begin to integrate the concepts that the AMC is really trying to examine when they give you that question. All right. Now that I said that, does the sort of learning objective for today kind of make a little bit more sense of sort of what a Chem Phys passage really is about and what you can start to do when you approach passages as you practice to sort of think through the patterns and the integration of content, Andrew?
Yes. Thanks,
All right. All right, cool. Awesome. Anything else you want to share?
No, that's all. I think you said everything for now.
Okay, cool. Awesome. So I'm going to pause here real quick. Thank you so much, Andrew. You can go ahead and mute yourself. So I'm going to go ahead because I've got until the 45. I'm just going to take any questions right now as I switch over my screens to the AMC, and we're going to take a shot at some of these questions. And if anyone wants to actually directly message me right now, because I actually do not remember who had asked me to, who had volunteered rather to do the question. So if you want to just step right up again, we're going to just try and do maybe 2 of the questions. It's going to be guided. So you're not in the deep end all by yourself. Anybody can volunteer, please.
I did.
Oh, you did? Awesome. Cool. So let's see. Let's find, do you mind just kind of starting with your name, obviously, and where you are located? And any additional information you want to share with us?
I'm Matita. I've been at a few of your sessions.
Oh,
and I'm in Madison, Wisconsin.
nice. I think, did we talk yesterday? Did you actually like?
Yeah, I did. And the day.
Okay. Oh, wow. Okay. All right. Yeah. So for everyone that's on the call, these sessions are a running series of content, strategy, advising, coaching type of session. So we're going to do a question together. Let's see if we can find a good one. So what is the magnitude of the electric field used in the MALDI described in the passage? Yeah. Skip that one. Skip that one. Oh, this is a good one. All right, cool. So what do you think about this one?
We can do that. Yeah.
All right, awesome. So why don't you take a look at it and just kind of tell me what you think about it?
Okay.
What do you think the question is asking?
Okay. Let me read it. Okay. It's saying which feature of the MALDI-MS technique allows, essentially allows like ions to separate.
Okay. So what do you think in your mind, if you're going to predict what the answer looks like, what factor do you think the most important factors that kind of affect this would be, right? So the experiment is about, something that's going to allow ions to be separated, right?
Mm-hmm.
So let's come over here and just think. All right, so this is going to be our like thought bubble, right? What do we think are some things that could cause? So I got kinetic energy might be one, right? Maybe it's the kinetic energy of something hitting the particle. What other ideas do you have?
Separation, speed, velocity, like.
Right. So think back to here.
Okay.
Right. Let's go back here, right, and walk through the experiment, right? So this is something that sometimes trips people up, right? You looked at the question and you stopped and you never look back at the experiment. Keep in mind, we haven't read the passage either, which is making it even harder for you because some of the answers are really right in the passage, but I want us to kind of think through, okay? So let's kind of walk through, right? So we have this electromagnetic radiation, right?
Right.
So what's the equation we're going to use to kind of figure out how much energy we got there?
E is equal to HF.
E is equal to HF, right? Cool. So we know how much energy is there, right? And then we look down here and we read, and it says that basically that DHB, remember that DHB we had written down at the bottom? The DHB, the stuff that was coated on the plate, it basically gets ionized, and what it's going to do is going to kick off one proton, or sometimes it's going to kick off two protons. Right? And then those protons are going to stick to a protein, right? So quick biochem question. What kind of amino acids are those protons, those ionized protons, sticking onto?
The acidic ones and the basic ones.
So what charge was on the ion that was produced? They produced free protons, right? What's the charge on a proton?
Plus.
Plus. So if it's binding to an amino acid somewhere on a protein, what's the charge on that amino acid got to be?
Oh, negative.
Negative. So what kind of amino acids might these be?
Acidic.
Which are? Give me some names or codes.
Aspartic acid and glutamic acid.
Aspartic acid and glutamic acid. So DE, for anyone that doesn't know this, aspartic, glutamic, A before G, D before E. All right, awesome. So this was like a weird little aside. Let's get back to the passage. So basically they used some light to ionize that DHB, right? And that DHB lost a couple protons, and those protons got stuck onto the protein, right? And so what do you think is going to happen to those protons that now have extra positive charge, right? Let me clear so we can see. Now that those proteins, right, have that extra positive charge on them, and we put them in an electric field, what's going to happen to that proton or that protein? What's the electric field going to do to it?
Is it going to deflect? I don't know if that's the correct terminology.
It's going to apply a force on it.
Okay.
Right? So do you remember the equation K Q1 Q2 over R squared, or sometimes like people like to say Q times E? What Q times E says is if I have some kind of charged particle sitting in some kind of field, electric field, how much of a force is going to be created on it, right? I'm saying force because guess what's going to happen to that little protein once it's got a lot of charge in it, right? If this side up here I told you is more negative and this side at the bottom is more positive, what direction do you think those little proteins that now got all that extra positive on them are going to move?
Toward the negative.
Towards the negative, right? So we got, let's synthesize together what we've got so far, right? So we're going to use some electromagnetic radiation in order to ionize some protons. And those protons are then going to coat the protein, right? And that protein is sitting in an electric field. We know electric field is going to do what? It's going to generate a force on that charged thing, right? And that's going to cause it to do what? It's going to cause it to move that direction, right?
Right.
Now that it's moving, right? Remember, do you remember what they were looking for us to analyze in this passage?
Electronegativity? Is that what
it was at the very top. So they said in the passage, there's something that they wanted you to analyze. I'll scroll up for you to take a look.
I didn't read the passage.
Right, so I got it right here in front of you. It's the first sentence.
Proteins, protein fragments, and peptides.
All right, cool. So you're looking to analyze protein fragments, protein peptides, or proteins and peptides, right? So you're looking to analyze something about proteins. What are some like things, some qualities or properties of proteins you'd be interested in finding out?
Their charge.
Charge, and what else?
Size, maybe.
Size.
We
can stop there. Yeah, we can stop there, right? So would it surprise you to find out that the goal of this experiment, right, was to set up a situation in which, remember all the things that we talked about, right? Remember initially we started thinking about electronegativity and some stuff about redox, right? And then all that stuff we talked about, it comes together, right? Remember when we talked about colors and the energy of a photon?
Right.
Right, this is where it comes together, because in this experiment on this passage, right, they were going to use electromagnetic radiation, right? That's E equals HF.
Mm-hmm.
In order to ionize, we already talked about it ad nauseum, all the concepts that get captured in the idea of ionization. In order to ionize that DHB, once you ionize that DHB, you're going to release a couple protons, which are going to stick onto a protein, right? Now you've got charge around that protein, and then you're going to accelerate it through an electric field. It's going to move towards this other beam, right? But how fast it gets there, those little chunks of protein are going to depend on how much mass each protein had, and did it have one or two or more positive protons, charge, right?
Right.
So what were the two things that you said you might want to really know about a protein?
Charge and size.
Charge and size, right? You notice how the experimental setup ultimately was only testing and trying to prove to you and tell you something you already knew, because it's an informational passage. They wanted to inform you that if you're trying to analyze proteins, you can check for the charge or the size. They informed you by presenting an experiment that utilized electromagnetic radiation to ionize a particle, to coat a protein, to accelerate it through a charged field, in order to be able to say one protein got there faster than another because its mass and its charge were different. Because again, they ultimately were looking to analyze these factors.
Got it.
All right. Does that bring it home?
Yes.
All right, cool. Awesome. So why don't you pick the answer for us that you think might be the right one, and then we will call it an evening for today.
B.
Why?
We just kind of talked about it. So we just talked about how, well, you just kind of mentioned it when you were talking about the mass and charge, but you talked about how that would essentially depend on the speed.
Okay, cool, perfect. And what about C? What do you think about C?
Well, time and velocity are...
So let's not think physics, let's critically think, right? Now we've got two ideas, velocity and ions, right? So what was I looking to analyze?
Wait, repeat that again, sorry.
What was I looking to analyze in this passage, the researcher, right? They're looking to see the charge size difference, right? So what's like the easiest, like most common sense way that you would, like if you were sitting over here, that's you, smiling, and your job is to say, what's the mass charge ratio of whatever protein, right? What's the easiest thing that you would look for? Like, how would you think through this problem if you were told sit here and answer the question of what protein has what charge and size to it? What would you do first? Like intuitively?
Like electrophoresis.
No. Like you literally are standing here, actually standing there physically, right? And you're told, as this experiment is happening, tell me what the charge size ratio is, right? I'll tell you what I'll do. I'll sit here and I'd say, who came in first? Who came in second? Who came in third? Who came in fourth? Because if you came in first, you're light or your charge is low. If you came in last, your charge is high. If you came in last, you're probably heavy or your charge is very low.
Okay.
Why would you come in last? Because it took you the longest time to get there. Why? Because you were heavier and your charge was lower, right? So if the amount of time to get there, right? If it takes you a long time to get there, what do we know about your mass? Is your mass high or is it low?
It's high.
Your mass is high. If your time to get there takes a long time, what do we know about your charge?
It's low.
Your charge is low. right? So I just kind of walked you through this, not to say that the answer choice you picked is wrong or right, because I'm actually not going to look at it. But to just kind of walk through the critical reasoning perspective, the critical reasoning points of how you can just stop and think through and say, okay, cool. How would I know which one was the bigger protein or which one was the smaller protein, right? The way you'd find out is by saying, okay, cool, which one showed up first, right? Same idea that you get in what biomedical or biochemical lab technique. What lab technique in biochem kind of does the same thing I just talked about. What's that mass to charge ratio?
Electrophoresis?
Electrophoresis, yeah, gels, right? Or SDS page, right? Again, a lot of these concepts cross over between biochemistry and different topics in chem phys, right? But you always have to start off from a point of knowing, you know, what type of passage am I looking at? What type of question ultimately am I trying to do? And if you spend time doing practice passages and not just relying on content, it's going to become easier for you to recognize the patterns.
Right.
All right. So thank you very much for helping out. And I'm going to go ahead and switch back over to my PowerPoint presentation. This is the end of today's lesson. I'm going to be around for a few more minutes to just answer questions, but this is kind of all I had today. I hope you guys enjoyed and learned. Stay tuned. However you found out about us, email us if you're interested in getting today's recording. And we are going to be doing a few more physics specific sessions this week, a couple chemistry ones, and look out for an AMC full length 1 free group review towards the end of the week. So thanks guys. Have a wonderful evening. And I hope to kind of see and meet some of you guys again, maybe in the next coming days.